So you can find that here, the wiki link. What I wanted to discuss more was where the direction things took and sort of lessons learned and things to take away for the future. So, of course, the charge of the working group was sort of reinterpretations of LHC analyses for BSM. That sort of eventually, in this group, as opposed to the previous working group we just heard from, so took a direction into focus on the reuse of standard model cross-section measurements for BSM in this week. So I discussed this last week, but a quick, very one sentence reminder. When we talk of standard model cross-section measurements, say like W plus jets or Z plus jets, we're not really saying that we're measuring Z plus jets and that's all you can really use this for. What we're really talking about is measurement of a particular final state, so maybe dilepton plus jets or single lepton plus met plus jets in a well-defined fiducial region that's hopefully dominated by a single standard model process that has other small backgrounds that fake that signature that we subtract off, with the uncertainties on that modeling and subtraction propagated through to the uncertainties on the measurement. And then we correct this measurement for efficiency and detector resolution effects to provide a particle level cross-section of that final state. Now, of course, if you have a new BSM model with that same final state and happens to pass the selection cuts perhaps by coincidence, say if you have a Z dilepton invariant mass cut around the Z mass, but if your BSM model happens to fall into that fiducial region, then you can use these standard model measurements for reinterpretation. And I discussed last week as well an example of reuse of these already in recent differential cross-sections of MET plus jets for dark matter models and so on. So there was earlier at the end of last week a discussion about a new BSM dark matter model that would result in both a MET plus jets and a lepton plus MET plus jets final state. And we discussed that this was a good use case for picking up the W plus jets differential cross-section measurements and MET plus jets differential cross-section measurements as just two examples. Others may exist. Picking up the data, picking up the standard model prediction, rivet routines that exist for both, and then plugging in your BSM prediction and seeing what you get. So it seems that, well, I'm going to show you quick results, but there's a lot in the backup which you can look at on the Twiki afterwards if you want more details. But we can see that this is doable from 0 within the week while people are still attending the rest of the sessions. So these are the differential cross-section measurements that we use. There's lots more in the paper, but they're picked out essentially one distribution at a time from each of the two papers just to look at it as a first stage in the analysis. So the main thing, I think the main hurdle to get over in doing this BSM interpretation is, of course, just generating the signal events. This was done for the first time this week. So the two of them have generated single jet production plus lepton plus dark matter pairs, and also two jet production in their BSM model. And this is what the jet PT spectrum looks like for the sort of W plus jet PT distribution. So they did have one question as to whether there's something wrong going on with matching here. Jet 1 PT from one jet production and jet 1 PT from two jet production added in, whether this is okay or not. And they're still looking into this. It's early days, of course, so bear in mind this. But obviously, if you have a BSM model and you want to look into it for RICO level searches or standard model searches, of course, you have to go through this kind of procedure. But nonetheless, bear in mind this is a first look at this kind of data. Also, one stage involved in this reinterpretation is getting hold of the proper uncertainties and the covariance matrices. For the W plus jets results in HEPdata, these results were provided as shifts, systematic shifts in percentages from various systematic sources that were then rebuilt into the uncertainties. The uncertainties in the shifts were rebuilt to make the covariance matrices that could then be plugged into the statistical framework coming out of Rivet. There's more details in the backup. And then once you've done that, you can add on top of your BSM prediction, the standard model prediction, and then do a comparison to the experimental data. So here we have the black points of the experimental data in W plus jet's final state as a function of the leading jet PT. And then here in the red and purple are one particular parameter set for this BSM dark matter model compared with the W plus jets standard model cross-section data, where you see that, okay, even with a 1 or 2 jet issue, you still see that this deviates from the measured prediction here. So this is actually enough, more details in the backup, enough to rule out this particular parameter point in this model, just with the W plus jet single leading jet PT distribution alone. Similarly, this is very unique, bleeding edge of study. This has also been looked at in the Met plus jets final state, and you can see again the same kind of thing here. This is actually a ratio on the y-axis here of Met plus jets standard model plus this BSM model injected divided by Z to dilepton plus jets standard model. And again, you see some deviations, but again, this is still under check. It's very, very early days. But you can just see, even from a single distribution in one model, in one measurement, or a single distribution from another measurement, you can start to exclude or find points in your parameter space that are consistent with the data. Potentially more power from combining this distribution with this distribution, and combining these two distributions with other differential distributions that are measured in these papers as well, which hasn't been looked into yet. And the beauty of this whole approach that I discussed last week, so I don't have my slides today, is that you can, when you have the covariance matrices and you have the vectors for your data and your standard model and your BSM predictions, you can really just chain these together very simply without doing much else. There was a question earlier in the week of how long this took. So just polling the authors, the time taken in total from learning how to do this from scratch to actually getting results was about 1 day integrated time. Generation of the events took about 30 minutes, or 10K events, and running this whole statistical framework and so on in Rivet took about order minutes. Of course, you now need to do this scanning over your parameter space, but it's computer time, not human time. So this is quite light in terms of ease of reinterpretation as well. It's kind of nice to see. This is the first time we've seen this W plus jets data used to set limits on this model. So most of my talk now is just lessons learned, recommendations, and so on. So lessons from this standard model reinterpretation for the first time with external people using our data. Most people are doing this recommendation, but I mention it anyway, just for completeness. At the absolute minimum, experiments need to provide the data measurements and the uncertainties of differential cross-sections in HEPdata. That's happening most of the time, but for older measurements, that might not always be there. Recommendation is to provide HEPdata tables for the standard model predictions in each bin of the measured differential distributions as well to aid reinterpretation. So, for example, in this paper, the data measurement is here. The red is the standard model prediction, and then these various curves are BSM predictions. We did provide the data and the standard model predictions. This is fairly new. This paper comes from 2013, I believe, and you can see that there's, again, data, a variety of standard model predictions here that take a huge amount of CPU resources, time, human time for validation and so on to produce. And of course, there's a physics message in the paper describing the use of these standard model predictions. And you can see that they vary quite a lot. In some cases, you have a lot of space here to fill in with some BSM interpretation to match the data at high PT. In other cases, there's already an excess in the standard model. However, in this paper, the standard model predictions that so much time was spent producing are not published in HEPdata. So this was a hurdle to reinterpretation that can be got over because you can digitize these plots, but it just is a bit absurd to have to do that. So this is an additional recommendation, which is something rather subtle but easy for the experiments to do in future. So to provide the standard model predictions and going further, multiple standard model predictions, because as I say, that you could provide this one or this one, and your reinterpretation might result in a different interpretation of the data. So having all of them, as well as the systematic uncertainties associated with these predictions in HEPdata, would add a lot of value for reinterpretation. Actually giving the sign shifts of the scale and PDF variations on these predictions would also be valuable in building the covariance matrices to give more accurate comparisons. A follow-up related to this is how do we treat the standard model prediction? In the reinterpretation, we take the data, we take the standard model, we take the BSM component, and then we make some statement on the validity of the BSM in that particular parameter space. if we provide more than one prediction, we can actually look at the span of theories. So you can always say that you pick this one because you believe for some reason that it's the best prediction for some complicated reason, or you can say I'm going to just rerun my analysis 5 times. It's quite light in terms of CPU, so it's relatively easy to do that if that information is provided. The really key thing is just to be transparent about that, and then people can make up their own minds about the conclusions you're drawing from the data. Of course, if you find that your exclusion doesn't really rely on the particular standard model input, all the better. One thing that's, of course, apparent from these kinds of distributions is that it's not necessarily optimal to take data as a standard model. It's a reasonable assumption, because in one case it's going high here, in one case it's going low, so you might say I'll take the standard model as a kind of reasonable baseline for my standard model, but really if you want to get down to fine detail, you want to at least look at other theory predictions. Other lessons of reinterpretation, when we're discussing the implementation of this with Andy, for example, is to provide these standard model predictions from the experiments as a separate file in HEPdata so that you can, in Rivet, easily switch between them. Right now it's a technical issue that means that that's not really very easy to do. And also a recommendation is to provide the statistical covariance matrices for data distributions, that is the correlations between different differential distributions. So in this result I talked about earlier, this is a exclusion based on just the leading jet PT. Now you might find that there's another distribution in this paper, such as the dijet invariant mass. You might find that you get some sensitivity to a different area of parameter space from that distribution, and that by combining that distribution with this distribution and performing statistical analysis across both simultaneously, you get even more exclusion power. But you can only really do that accurately if you know the statistical correlation between perhaps that 300 GV bin in PT and the 1 TV bin in dijet invariant mass. This is impossible to do after the fact. This can only really be done in a model-independent way by the experiment. You can bootstrap the data as you produce it. And it's really simple. I mean, if you have access to the data, you can do that in an afternoon. After the fact, it's not possible. So we lose that information, and we lose that ability to add some sensitivity to the reinterpretations. So this is something for the experiments to think about. It's not always presented so far, because in a lot of cases, these standard model measurements were not done in the mindset of allowing reinterpretation, only standard model tuning, where it's not so important to have those. Although, actually, Andy tells me that even for the tuning of the standard model of the generators, that information would also be handy. So it's something we should really be thinking about from the experimental side. Related to the point about the theory uncertainties I mentioned on the previous page, similarly for the experimental data, we should be providing the systematic covariance matrices, or perhaps better signed shifts from which the covariances can be derived. That's not always the case. And a follow-up related to this is that it would be nice if there's some level of agreement within the experiments or between experiments on what to group and what not to group. Do we group jet energy scale systematics? Do we group other sorts of systematics? So we can find some kind of consistency between experiments if you wanted to combine differential distributions between CMS and Atlas, for example. A few other reinterpretations considerations that came up during the 2 weeks for follow-ups are a comparison of the sensitivity of simplified likelihoods versus unfolded distributions versus RICO level searches. That's something we would like to study, but didn't manage to do during this workshop. Also, as I touched upon, quantifying the sensitivity of reinterpretation in terms of BSM models against standard model cross-section measurements for a single distribution, combining with multiple distributions in different channels, and perhaps cross-experiment. It would be really nice to see some sort of systematic studies of the gain, if any, that you get from this. Initial studies that have been done from the theory side, purely on Monte Carlo, have said that you can potentially gain a lot from combining different channels and different distributions, but it would be interesting to really see that done with standard model measurements. There's also these questions about statistical questions of the use of unfolded data, what happens to our sensitivity in the limit of no data, limit of no standard model, and limit of no expected BSM. Do we run into statistical problems of the validity of the reinterpretations? and the model independence of these reinterpretation approaches. If we use W plus jets data and we use it where we have an additional lepton that we don't see, does that cause us any problems, for example? Is there any issue if we have a resonance in a distribution? Has that been taken into account in the uncertainties that are assigned for model dependence on the experimental measurements? So exploring the limitations of the standard model cross-sections is something that hasn't been explored that much. Although in principle these things are model independent, we might find some extremes where that's not true. And what do we do about unknown correlations between measurements separated by time and data sets and experiments? So one thing I was talking about was combining W plus jets and Met plus jets, differential cross-sections, for example. And there you might ask questions about if you want to produce a huge covariance matrix now that correlates a bin in your Met plus jets distribution with a bin in your W plus jets distribution, how do you handle the correlations in jet energy scale between those two bins in distribution? You could assume they're fully uncorrelated, you could assume they're fully correlated, you could do something in between. To some extent we don't know the answer unless we go and repeat all these analyses, which you might do if you really find some interesting region of phase space in a particular final state which seems to be compatible with some high significance in a reinterpretation analysis with a BSM model. But before that, you're really not going to know these correlations. So a recommendation to be discussed, at least we said for now that of course you can take the possible extreme correlations and test the dependence of whatever interpretation result that you get under various possible extreme correlations. So you just, in this huge matrix, just inject various correlations and see how they affect your limits. If your 4 sigma deviation from the standard model relies on a particular correlation scheme between 2 differential cross-section measurements, you might be concerned. If it doesn't, that's very interesting. Nonetheless, you probably want to mention that either way, but we've got to be very transparent again about the assumptions that have gone into these combinations. A few more technical things we came across in doing these reinterpretations were some issues with HEPdata that were, I think, previously not discovered. So I wanted to mention them now because it's a lesson, is that one thing was data loss. So we produced these measurements of W plus jets cross-sections in 2013, 2014, and there were 36 tables of cross-sections attached, and then a little link here that just said in small letters, these are all the covariances, by the way, that are really useful for reinterpretation. At some point, the back end for this website got updated to a new, much better website, but this information got lost. We noticed that if you went to this new web page, all of this information, which has some sort of monetary and human effort value to it, has completely been lost. So if this website died, it's still active. If this website died, in principle, that covariance information would be lost. This only got picked up because we started using this data for reinterpretation. Another issue, slightly different, is data entry issues. We noticed that in the covariances, once we managed to recover them, that the luminosity uncertainty in descent actually varied across bins. I mean, it looks like maybe a rounding error issue, but while this is not maybe so important, it does raise concerns about the validation that goes on in these auxiliary data files that perhaps until now haven't been used, or maybe people don't care. It's a bit strange anyway. The thing I wanted to take away from this is it's important this data is actually used to some extent, otherwise why are we producing it in the first place? Okay, you get the first bottom line result in the paper, but hopefully this data is usable. We want this data to be used for more than just that one publication. It costs a lot of money to produce that data in the first place. Reinterpretation actually provides a useful service to the community in providing cross-checks of the data. You don't have to actually go out of your way to produce cross-checks. You just, in using it, you find something odd. It's just extra eyes on the problem. This is easy to fix if problems are found early. If you find this problem 5 to 10 years down the line, it's essentially impossible to fix because people are like working in a bank now. So the earlier we spot problems, and this relies on people actually using the data, well, the better. The recommendation then is first to make sure that the development of digitized data, standard model predictions, and any auxiliary material like covariances and so on, introduced earlier into the publication chain. I think in a lot of cases, especially historical cases, this has happened after the papers have been published. This is improving, but this is something that needs oversight. Could it benefit in some ways from at least within a group? common tools for conversion and common formats for output to help make sure that this is produced early and that people aren't reinventing the wheel. And a follow-up is really how to best validate this. You can have human error when checking hundreds of numbers here by eye. People's eyes are bound to glaze over at some point and not notice that this number is 1.9, this number is 2, and it should be 2 and 2. And how do you know that this number shouldn't be 0.21, not 0.22? Can we have some kind of automated validation, something to think about? Humans are going to fail on order a few hundred numbers, real numbers to check. So something to finish up with is for standard model reinterpretations in future. So you've seen one use case that's been started now of use of W plus jets and Met plus jets data for dark matter searches. Are there any other use cases of standard model data that people would like to explore? Are these generalized searches like Met plus jets valuable? And then sort of jumping off that, what final state particle level differential spectra would the community like to see? Are there final states that have not been measured, differential cross sections have not been measured, which would add a lot of value to searches for BSM? And just an open point, if there's anything I've forgotten to mention people want to add, please do so. Okay, that's it. Also separately, a PhD.